a very good morning to all the participants. So, once again, it is our great pleasure to welcome you all to the International Conference on Recent Developments in Material Science Application. So, our Chennai technology has been started in the year 2010 by our Honorable Chairman, Sri Sriram. And today, our institute is on the top second position among all other private engineering colleges affiliated to Anna University in Chennai, in Tamil Nadu. This recent listing, the recent ranking was announced by Anna University last month, which states that we are in the top second position among all other private engineering colleges in Tamil Nadu. So, the material science application, which is one of the great fields. So, this great conference today, we have Mr. Pravin Luthada, who is the co-founder and CEO of Addcomposites from Finland. It is our great pleasure to welcome him for this conference session. We welcome you, sir.
Thank you. Really wonderful. I'm really happy to join. And this is just I have to say, I love Chennai food. I've been to like Sriharikota and mostly in that area. It's just awesome. But just to like really thank you all for joining to listen to this. And this is something I don't know. So I would go with this basic understanding is that composites is like, sorry, please.
Yes, sir. And so let me, let me, as the so we want to introduce you to the forum and we learn about you. The forum should understand. And for that, I call Ms. Sapna Sai to introduce our expert to the forum.
Yes.
A very good morning to everyone. Mr. Pravin Luthada, co-founder of Addcomposites, Finland. He did his bachelor's degree in mechanical engineering at OAST Bhopal and his Master of Science in Mechanical Engineering at Aalto University. He worked as a product engineering in Indian Space Research Organization for about 4 years. Currently, he is the co-founder and CEO of Addcomposites. His areas of specialization involves automated fiber placement and advanced additive manufacturing. He was awarded as the Gazetted Officer India by Indian government in the year 2011. He is an active member at Indian Society for Advancement of Materials and Processing Engineering since 2013. We are glad to have you, sir.
Thank you very much, Sapna. I think that was a bit too much of an introduction, but really, thank you. I'm basically an engineer, mechanical engineer, but okay. I think composites is kind of one of the areas that we work in. So I think let's get started with the presentation, at least that I put together. The main idea with the presentation today is the like the advancement of the manufacturing. That's kind of one of the with the composites and what's possible. So the title is continuous fiber placement and printing, but then it really requires a bit of a general understanding of composites. So that is something that I would like to just give firsthand. So composites are basically like you have matrix and you have reinforcement, and you combine both of these elements and you get like both benefits of both, and you have much better properties because you're combining these two properties. And why does it matter to like have really good materials and manufacturing processes? It's really critical for us to be able to take manufacturing to next level, because we really want to not only be, let's say, in outer space, but really like go beyond it. And manufacturing can really contribute it. And the key factor that really can enable that is digitized, sustainable, and efficient manufacturing. By that, I mean a manufacturing that is digitized is something that is like if you manufacture a part, let's say in India or in USA, that's going to be exactly the same because it is manufactured digitally without any human interference. So that way you have a part that is exactly same wherever you produce it. Then the sustainable aspect of it is comes in a way that you want to use the least amount of material to get the same amount of strength, and what happens if you do it that way, then you are saving a lot of material that doesn't have to go through the complete life cycle of a product, so getting used, thrown out, and then get recycled. So you save the material just by using less of it, so then it just that problem doesn't exist at all. Definitely once the life cycle is over, you want to recycle and reuse it. And by efficient manufacturing, I mean is like now you have a material and now you know you want to use less of it, and so you optimize it, and then you really want to apply it effectively. So you have to really figure out how to cost effectively do it. So don't spend a lot of money doing it. And so this is kind of what the plan is. How can you achieve that? So you definitely first choose a better material. So by better material, I mean like for each application, definitely there is a material, but you really have to see like for this particular application, can I somehow optimize to achieve the same level of strength and properties without using too much of it. So if there is a material that can be used less, please use that. Then applying them efficiently to manufacture part. I'll talk about this like in the later slides as well. And then you have to make sure you do the above. You choose a good material, you do a very good manufacturing, but then you really have to make sure that it is cost effective so that it really can go to industry. So everybody should be able to use that process to be able to actually make the manufacturing happen. So the first point is, as I said, so with that vision, you want to choose a better material. And definitely there are metal and metal alloys which are very widely used already. But I'm a big fan of composites because they bring in so much more than just, let's say, and simple metal properties. And in composites, there are basically three main types that are there that are very widely used. So once in one of them, you have the continuous reinforcement that is going through the matrix. And then the second bit is basically where you have the short pieces of this fiber, which is short fiber, chopped fiber, or you have some small even pieces of that you put in the matrix to make it really strong. And then you have particulates. Particulates are basically like, let's say, glass balls or some sawdust or something like that. And once I say matrix, it's most likely it is a polymer matrix that we are talking about here. So you have these three types of options. Let's say the easiest to use is kind of with the particulate. The slightly harder to use is with the chopped fiber. And the most hard to kind of manufacturing wise is the continuous fiber. That's why people don't use that much, but then that's kind of the overall aspect of it. So where to see, like if you are trying to visualize it, okay, what does continuous fiber composites or material looks like? So most of the plain body that is made today, or space components that are made today, are all, most of it is continuous fiber composites. Then whatever you see as mostly the body panels, I think most of the trains, marine structure, body side of it is chopped fiber, and that is reinforced with these polymers. And then you have particulate based, which is, so you have these particles that usually you would put in the plastic and then you inject mold it. So you can get really complex, strong parts, but then you can achieve really complex shapes. But then here you are just kind of creating the plastic waste. So once we talk about plastic waste, that's what the most of it is. So most of the plastic bottles are injection molded plastics and stuff like that. So like the key point, basically what I'm trying to say in the materials aspect of thing is that you you want to have you have the possibility to create from the same material. So let's say you take 100 grams of carbon fiber and 100 grams of plastics. Using the same material, if you use continuous fiber, you can effectively achieve 5 to 20 times of the strength and other stiffness based properties compared to the chopped version, or like if you're using just the glass balls or something. So you have that much potential. So once you can achieve that higher level of strength, then you have the capability to use that much less material. So you can have 1/5 the thickness of a part, and then that becomes that much lighter, and that opens up that many more applications. So this is the first point that you'd really want to choose if you're, let's say, developing or thinking about any parts. So try to think, where can I use more continuous, more best material? And that's the first step in the manufacturing aspect of the thing. The second thing, when I said about the digitized manufacturing, and that's where you have to really see, okay, what are the digitized form of this manufacturing that exists out there. So let's assume you have chosen the best material that is out there, that's continuous fiber, that is with the matrix. Then you end up with basically two digitized manufacturing methods. So there is continuous fiber placement, and then there is continuous fiber printing. So think of it as like how we fly kites, and in the kites you have a thread that is glued up or something like that. So there is a continuous fiber with a glue on it, and you are going to make a shape from that. And now these are the two approaches that you have. So with the continuous fiber placement, what you will be doing is like taking that strand or bunch of strands, and then we'll be putting them onto a 3D shape with application of heat and pressure. So what would this heat and pressure would do would definitely melt the matrix around the fiber. And then what the pressure would do will take care of the bonding between the layers and also between each of the fibers. So, and it gets it really homogeneous. So then you have, I have one image that I will show later, but it shows like it gets to like really, so all the fibers have good amount of matrix around them to transfer load and everything. That's what I mean when I say homogeneous bonding. And then you have basically, now from this fiber strand, you have created a shape that can actually be used in industry. The other approach, which is the 3D printing approach, you can take one of these strands, a bunch of these strands, and then just extrude like in a 3D printer, and then start to create shapes. And there is with the 3D printing, as we know, it does one layer in an XY plane or any plane for that sake, and it does that planar motion to create the shape. So like now you have these two processes. Now once you have to choose, once again, now you are choosing from a process. So let's say continuous fiber placement, because you're applying pressure and temperature and making sure there is a good consolidation, you are able to achieve very good fiber volume fraction. That means there are more fiber, which fiber is basically the reinforcement, so that is strength. So you have effectively much more higher strength. Then you also, because now you have much more better strength, you end up using much less material. And it's a as I said, it's a proven technology. So most of the aerospace and space components that you see out there, especially the big parts. So think of wing of the plane, a body of the plane, outer body, also the engine cowlings and everything. Those are all made with fiber placement. It's a proven technology, and it's since 1980s it has been proven to do this. Okay. So now this is continuous fiber placement, and then you have continuous fiber printing. That is what happens because once you're extruding only, you have a higher amount of matrix than fiber because you want them to stick on their own. So then you have much lower fiber volume fraction, and we are talking, let's say in fiber placement, you have getting about 60-65%. That's a very good range to get to. And whereas you have fiber printing, you can have ranging from 5% to 20-30%. You can definitely go higher, but you have to do a lot of post processing then. Then you have with the continuous fiber printing, because as you might have used some 3D printed parts, you can see the layer to layer bonding is really weak. So this has the same problem. Even though there are fiber in the planar section, they do not have, let's say, out of plane strength. So then they basically are very weak in that direction. And because it is done, the whole part is built in just XY plane built up. There is that weakness is there. This is something like continuous fiber printing now is becoming slightly more adopted for building larger parts. So let's say if you want to print a boat or let's say like some sports gear, which are, let's say, relatively bigger in size, continuous fiber printing is pretty good because then you can, with just plastic, you don't get the rigidity of the structure to stand on its own. But as you have continuous fiber in that, and the structure can now stand on its own and can create multiple of these applications that are there. These boards or whatever component that you end up creating, once again, are not the final part. They are usually prototypes because it's not well optimized still. Then this is just a rough approximation of costs that I know from the industry, at least in Europe. I'm really sorry, I only know the cost in euros, but definitely feel free to convert. So you pay for continuous fiber placement from 75,000 to 200,000 euros to get that one of those systems. Whereas if you go continuous fiber printing system, you're paying roughly the same price, to be frank, because fundamentally all the components are the same. So now here it's kind of overall view once you're making a choice from the economical point of view. But then this is what you actually get with each of the process. So these are just the microscopic kind of image, I would say. So you have on the left, you see the fiber placement based images that you get like a very uniform distribution. As you can see, all the fibers have resin around them, and then there is some bunching, but it's pretty equally distributed. Whereas on the right side, you see the continuous fiber printing, which is like really a chunk of fiber that has no resin at all, and then you have basically a bunch of resin put together, and they are like pockets of each other, and there is like, yeah, it's just poor because there is no control in the way how the fiber and the resin are coming and heated and are applied. So that's what creates this inhomogeneity. Something it's not homogeneous in its strength, and that starts to create a lot of microscopic issues with the failures. So just to kind of maybe sum up, so now coming back from the materials that we wanted to choose the best one, and then manufacturing process that is the best one. So now you're choosing the best of the best. So you're taking, okay, you're going to choose the continuous fiber and matrix, and you're going to use, let's say, fiber placement as a method. The third big thing that you want to solve is that how to make this really cost effective. You want to really get to the really good quality, but then you really also want to make it go really big. So create a really big impact. So here, to create a mass market impact, then you have to find applications that are not just in aerospace. So now we have to, like, a lot of automotive and a lot of I would say marine-based applications that are coming up for such products. New space is also something that is start to utilize this a lot now. But then more applications you find, the more better, you can tweak it for that market really well. But then I will show about these applications also in later slides now. Then you have the possibility, once you're thinking of such, let's say, processes, to make it really adaptable, you can actually use existing, let's say, the machines that are already there in the manufacturing plant. So I have actually very good experience. I visited, I think, Ernakulam bunch of time, and then there is also like a lot of factories around Chennai. And if you go to those factories, you start to see they already have CNC lathe machines, and those type of machines are already there. So those are already really precise moving platforms. Now, if you can mount something like this continuous fiber placement head on top of them, you start to utilize that already existing asset. So you don't have to spend really huge amount to buy a robot or anything else. Then they start to utilize the existing infrastructure in a bit more meaningful way. And then the third bit to get to this mass adoption is choosing the material that is the most cost effective. So you want to have continuous fiber with matrix. So you just have to choose what is, let's say, available around you. So in India, we have a lot of naturally grown continuous fiber, and that can be bamboo-based, flax-based, ham-based. Then if you want to go for slightly better applications, you can go for glass. And then this glass is also very, very cost effective. So then you start to choose, okay, and never compare kilogram to kilogram price, because now you are creating structure that is 20 times stronger and lighter. You don't have to compare steel per kilogram to glass fiber per kilogram price. What you have to compare is that for the final strength, how much steel do I need and how much processing and all that it would take. Whereas glass would be needed only like 1/10 of the glass, and you will have much better structure. So you definitely have to create your own matrix around how would you choose this material for the process. So you definitely want to have a much better material in terms of cost, because then it makes it much more economical for manufacturer to opt for it. And so this is at Addcomposites. This is our approach. That's how we go about it. So we developed this fiber placement head that you see on the very left image. It's a plug-and-play solution. So you basically get this tool head. You can mount it onto any robotic arm that is out there. So it can be KUKA, ABB, Fanuc, or any robotic company, or Tata, whichever produces the much more better, much like robotic arms that are available. And now you can plug this robotic tool head into those, and then now you have a fiber placement system ready for you to work with. Hello, is everyone there?
Sir,
Hello.
yes, sir. Mr. It is audible.
Yeah. Okay. Yeah. So then, if you have chosen the robotic platform, then you have the basically the second biggest cost that goes into like building of this composites parts are molds, but now you can 3D print the molds. So you can just 3D print a shape and you can have from 100 to 1,000 parts made from that one mold that is just 3D printed. So you are not waiting a lot and then be able to create the 3D shapes in like at very low cost and still be able to create a very strong structure. And then the third bit that I believe is there is the software, because you really like in a 3D printing software, you have a slicer that slices the geometry. Similarly, if you have a shape or a part that you want to create using fiber placement, you need to have a software that can help you plan and visualize and how it's going to go without actually building up the things beforehand. And this is also a component of digitization. So with Addcomposites, you can get this basically for educational institutes, almost free tool that you can just use and plan and see how your part would be able to be produced using fiber placement. So that way, overall, you're like, is it feasible or not? So this kind of is our approach to make it like plug and play solution, use 3D printed molds, and then have a software that is pretty much open source and anybody can add to it. So just let's to kind of talk about the applications that if you have chosen a very good material, you have chosen a good manufacturing process, and let's say you are able to make it go cost effectively, you have so many new applications coming up that demands this because everything that will fly needs to be lighter and stronger. So starting from flying taxis to delivery drones to surveillance drones, all of them need to really have a lot of composites and continuous composites, because you really want to save every flying minutes that you can save, because these all things are going to be running on battery, and battery is basically a function of mass that it is carrying. So it will die sooner if you have heavier mass there. Then the other application that we see coming up is in the e-mobility, which is a bit more like you have bicycles with electric things in it and all. And that's where, once again, you can have much lighter bikes, and then can have much better functionality as well if you use composites. And then you have delivery robots that you would want to, which is like, at least in Western world, it's gaining a lot of popularity given the COVID and all situation of lockdown. Now it's becoming even more so that everybody's ordering their food. Like nobody is going to the shops physically. And this is something a bit more, I would say, more personal space, in the way that you can have sports equipments and more to human augmenting things that you can have. It's a like really good example of foil of the carbon that you can use to create these seaplanes. That's how they like to call it. Then you can have shoes that definitely gives you most of the energy back as you're running. Then you can have skeleton, which are basically kind of self-powered. So once you push on it, you basically gain from it. And then you have the I think this is one of my favorite, the bike that Edivo launched recently. It's completely made from fiber placement type of process, because it's completely consolidated. And then you have the, like everybody can customize their own, I would say, the vehicle that they are using. Then the next level of application definitely is going to be in the electric vehicles, where there is the battery packs, and then the all of the interiors has to be as light as it can be, because you want to save everything for that battery. And then you have the carbon fiber wheels. And this is a very critical improvement. I think a very good comparison is like if you have alloy wheel to a carbon fiber wheel, you see about 30 to 40 miles of difference in battery life for an electric vehicle, which is very critical for so many people, because everybody's trying to push for getting the maximum out of that car battery. And then there is definitely inbuilt displays in the cars now, and everything needs a back coating like your phone. And there is like definitely a lot of interest in lightweighting your phone. Or think of any consumer electronics. Everything is getting thinner, but it needs to stay still as stiff, as strong as it can. And so every of these components need a bit of composites to get to that stage where it is getting to the next level. We are way past metal in these cases. So I think this is pretty much to sum up that if you choose a really good material, choose a really good application technique, and make sure this application technique is applied cost effectively. So you are not using very extravagant material or so fancy process, just not approachable to many companies. So that's where the whole thing combines to. And then you have so much potential in terms of application that you would be able to achieve using using this approach. This is just one of the applications I thought would just brush over, but this is where I think both of the technologies combine together. So you have a 3D printed shape, and you know a 3D printed parts is not that strong, but think if you can put tapes from continuous fiber placement on it, then now you got the shape flexibility or creation capability of 3D printing, and then now you are able to strengthen that with the continuous fiber placement. So you are able to do so much more to that 3D printed part that now it becomes completely functional. You can fly planes with this approach. So you have a part that is built like this, can definitely fly. Yeah. And then on the left side, there is like a really good example of sole. So if you 3D print sole for your shoe, if you stamp on it, most likely it will break after 10 or 100 steps. And now if you can, once again, overmold it with the fiber placement approach, because of really good fatigue properties that composites have, you can run for miles and have much better, how do you call that, energy back from this sole, that you are able to achieve very good, let's say, individually suited soles that is, printable by everybody. So yeah, I think overall to say is that if we are able to achieve all of these three critical steps, then there is a lot of application that composites are able to like enable, and there is a huge potential in this area. And definitely, at least this is our thought process while we are building this whole system. But then if you have any feedback or any questions, I'd be really happy to answer. Or also if you feel like contributing towards it, just let us know if we can help with something. But then yeah, thank you.
Thank you, sir.
Yes, sir. Thank you. And sir, thank you so much. It's one of the thrust area in this era. And so I would like to share another point here. Since I have been requested by a very good journal to review a paper in fiber placement, and I have accepted. but because of business, I was unable to submit the review comments to the particular journal.
Okay.
And see, even though 2.5 months was over, usually other journals, if you are not getting review comments, immediately they will go for other reviewers and they will be finishing the chapter. But in this case, I have been repeatedly asked by the journal to review and submit the comments. That means the people, those who are working in the particular fiber placements are very less. I hope you can count the people. I hope. Yes, that's a very big journal, but still they are. I have also not worked much more on that. Just I have with my students, I have written a review purpose, and that has been published in one journal. So even though I have not worked a lot, I have done little work. I have been repeatedly asked to review the journal. That means the people are very less in the automatic fiber placement, and it is a very good area to go for research. And certainly, the expert speech like Pravin Luthada sir, he has given very good knowledge sharing. I hope this will help the research community to enter into the new research field, and hope this will be able to give us something. And also, I told all my students to attend this session since so next we were talking about 3D printing. Now we have come across 3D printing. Now we are talking about fiber placement. Okay. So in India, his lecture will be highly useful to the research society to go out with the researcher. Thank you so much for sharing your knowledge, and I hope since it is new technology, I hope people will take time to understand this technology and to put through the questions. And still, participants, if you are able to ask, if you are having any doubts, you can ask your questions. You can clarify doubts with Pravin Luthada sir. Please, you can post your questions in the chat box if you want to ask.
Yeah. Really, just in the meanwhile, the questions come. I think really thank you for having me. This is something I've been really want to do, to kind of talk about it a bit more, to get the knowledge out there in terms of like why it is so critical. I'm definitely not an expert, but I know something about composites, so I at least try to put as much information together through the blogs that we put out from our company's LinkedIn page. But that's pretty much it. Really, thank you for having me. Yeah.
Yes, sir.
Yeah.
So, Dr. N. Venkata Sairam Kumar, I asked you a question.
Yes.
Up to what temperature the performance of glass fiber perform?
Yeah, so usually if you have, it is a matrix question, then the question of like the fibers. So you can have glass fiber that is with thermoset perform up to 200 degrees Celsius decently, but after that it starts to get flimsy, be it thermoset or thermoplastics. But here is the like composites beauty. The most highest performing, I would say, temperature range, if you want to work, is about 4,000 degrees Celsius when you are basically re-entering from the atmosphere with the rocket. And the shield is made out of carbon ablative composites. So you have carbon composites, which is it is a carbon reinforced and carbon matrix that can perform very well at 4,000 degrees Celsius. It actually increases in its strength. So for that, if it is a high temperature application, I would definitely recommend using carbon. It's a bit expensive because the manufacturing of it right now, it requires a CVD type of processes. But then if you just want to use glass fiber based composites, I think 200 degrees Celsius to 300 max, I would recommend. I think even 300 is a bit pushing there. Yeah.
Thank you, sir. Still, anybody wants to clarify a doubt, you can unmute your mic and so you can clarify a doubt. Okay. And Dr. And very much, very much, answer. Thank you. Thank you.
Ah,
And
pressure. Oh, yeah, this is a very good question, to be frank. So for continuous fiber placement, you're actually aiming for about up to 1,000 Newton force when you're applying it. You don't have to go for, so it's a like in thermodynamics, how we can compensate temperature for the pressure. So if you can melt it well, you don't have to apply that much pressure. And also, if you can apply a lot of pressure, you don't have to melt it that much. But the good balance is like if you are able to get, let's say, a good thermoplastic PA6 or a peak based, let's say, carbon fiber peak composites. For that, you need like a temperature of about 400 degrees Celsius and a pressure of about 7 to 800 Newton applied on top of it to be able to achieve very good bonding properties. But then you can definitely have lower temperature a bit, but then apply a bit more pressure to achieve it. Just like slight balance there when you are going to be using something like this. Yeah.
thank you. Thank you, sir. Thank you. And, any other questions? Yeah. Thank you, sir.
Thank you. Yeah.
Okay. So if there is no question, we will wind up this. So participants.
Yes. Yes. It's also, yeah.
So,
Yeah.
so could you please,
Yeah, audible, sir. Guruzan sir, audible. You can put the
manufacturing continuous fiber, we need to prepare the preform, right, sir?
Yeah.
Could you
Yes.
please explain what are the challenges do we have to face, particularly when we are preparing the preform, and how to overcome that?
Yeah. So I'm assuming like if you want to make continuous fiber preforms,
Yeah.
so there are continuous fiber preform can be in the dry format, which is just dry fiber placed to create a preform that you would put in the RTM mold and then inject the resin to it. And then there can be thermoplastic preforms, which are basically blanks of thermoplastics. So just for the dry fiber preforms, the main challenge is that once you have the, how do you say, the binder that you're going to use in the fiber, first of all has to be compatible with the resin or matrix system that you will be using. And the second key property that you have to keep in mind is the breathability, or like how fast you are able to infuse it, because that's very critical to achieve a very good impregnation, or let's say homogeneous impregnation in the preform that you have created. So just the choosing the good binder and choosing the right channel strategy for flowing the resin into it would be able to give you like really good preform quality, I would say, in the end. Definitely you have to keep your fibers straight and place them really well, but that is a very big mechanical challenge.
But as far as in the choked fiber, it takes we will be able to fabricate the product very easily. But
Yes,
this continuous fiber, it takes a huge amount of time. We need to.
yes, yes. Yeah, and that is where like a bit of a mechanical engineer process know-how comes in. If you choose your channel strategy properly, there are now different strategies, so you don't have to have the infiltration of the epoxy from the only from the borders. You can have it from the center of the channel, or have multiple channels where you create the strategies to infuse the preform that you have created. Uh, so I think it's a bit more of a mold design challenge than the material challenge. There is one more strategy that is about the channel design. So once you are creating your pre, you have to think of, can this can there be a bit of a fiber gap where you can use that as a channel for making your resin flow go faster. I definitely agree, because the chopped fiber, the nature of they allow like automatic channel building fast execution.
Thanks a lot, sir. Thank you.
Yes, sir. Thank you, sir. Thank you so much for your presentation, and I hope some of the participants are from our LinkedIn also. So I thank them also for joining the wonderful session. So thank you, sir. We would like to hear you a lot in some other occasions.